Just count by threes. Yeah, so if it's
So between problem 9 and 13, every circle?
9, 12, 15, 18, count by threes, yeah.
From that date? Yeah. I have no idea. It's like, yeah, I'm pretty sure it's fine. That's all I have.
Alright, so let's see. So for those of you who are saying, chapters 4 through 7, holy crap. There are books that have a chapter 2 that have 12 sections in it, right? Some of these chapters have 2 sections in them, so be sure you know what you're griping about before you start griping about it. There's not a lot of sections on this next test. So again, just reminding you guys, probability will not be on this next test. That's why I have its own little double quiz thing. It's its own little thing. This test will start with that XP of X stuff, right? So we did the XP of X stuff, we got the mean, standard deviation, then we did binomial stuff was kind of like the next big thing, right? What we just did last time, and then we got a little bit into uniform probability, which is one kind of continuous probability. So what's the difference between a binomial, which is discrete? Why do we call a binomial, why do we call it a discrete distribution? Yeah. Because what's a binomial? Give me a situation that would be binomial in nature. Give me a situation that would be binomial. I love you guys. Think about anything we've done with P's and Q's and N's.
Has hair, doesn't have hair.
Say again?
Has hair, doesn't have hair.
Cat's got hair, cat doesn't have hair? Is that what you
Has
said?
hair, doesn't have hair. I didn't think that much.
Oh, okay. These poor little bald cats, but there's a whole species of bald cat. Dr. Evil, all that kind of stuff. Sure. You could say the probability somebody has hair, doesn't have hair. So if I take 30 people, I want exactly 2 of them to not have hair, right? That kind of thing. So it's 1, 2, 3 people. You can't have 2.5 people because somebody shaved half their head. You still got hair on half. You got a little tuft here, still hair. You still got hair on your head. It's got to be completely bald or something. You guys with me? There's no in-between numbers. That's why it's discrete. Discrete is 1, 2, 3, or even 1.5, 2, 2.5. It's got to skip an infinite number of numbers, really. Continuous could be anything in the range of between something and something. Anything in between there. It doesn't skip anything. So it could be 1.78, 3, 4, 6, 5. You guys kind of with me? So that's why with binomial, we can draw them like this. Right, this would be 1, 2, 3, 4, 5 maybe. Continuous, we can draw them like this. Nice and smooth because I don't skip anything. It's a nice smooth curve. I would still say that this is roughly that shape, wouldn't I? But I can't exactly use the same things here as I can here because this is discrete data, this is continuous data. Alright, maybe. But the one thing these guys have in common that we got into a little bit last time was the idea that the area, if I draw a picture that represents the probabilities, and the total area of the picture is 1, then if I wanted the probability of this, I just find the area of that. You guys get that idea? And I sort of did that thing with the dartboard, the area related to the probability that you're going to hit that part of the dartboard, that kind of thing. Okay? So just to remind you guys what we did last time. We will do a little bit of a review of the binomial stuff too here in a minute with a little handout. It's going to lead us into normal distributions. So can somebody tell me this? It's going to be a very strange question, and you know that I don't care about that. Is this a valid probability distribution? Yes. Why? Yes.
The area is 1.
Area is 1. What's the area of that rectangle?
10 times 1.
Yeah. How long is this? 10 times 1/10 is 1. It's a valid probability distribution. So if I want to know any probabilities of a subset of this, I just have to find the area of that. So the probability that it's something between, that's good, Jeff, put a 6 there, between 9 and 10, what would this probability be that is between 9 and 10? Yeah, the width is 1, times the height is 1/10. 1 times 1/10. 1/10. I love it. So that's kind of like the last thing we did last time, was we got into this a little bit. I really want to stress this idea, though, because it totally carries us through most of what happens next, is that the area, if I draw a distribution, if I draw it, and we've been drawing distributions for a while. Remember, we've done relative frequency distributions way back when we did histograms, right? If I draw it and the area is 1, then the area of any small piece of it will relate to the probability of that event happening. So this area between 9 and 10 is 1/10, so the probability that I get between a 9 and a 10 is a 1 out of 10 chance. Okay, maybe. So if I had some random number generator, generating numbers between 7 and 17, there's a 1 out of 10 chance that they'll generate something between 9 and 10. And when I say that, I mean it's generating stuff like 5.629973. Well, not here, there's 7.629973. Stuff like that. It could generate any number, any decimal, however long, between 7 and 17. Yes, ma'am?
So what does the 1 signify in that little equation there?
The width of this.
Okay.
Because and again, please realize this is, on one level, this really is just an area of a rectangle. So that's why uniform distribution is one of the nicest freaking distributions you can have. If I gave you this picture and I said, how tall is this distribution, could you tell me? How tall must that be to make it valid? 1/3. Where'd that come from? Because the width is 3, I got to multiply by it to make it 1. Don't make that any bigger deal than that. It's got to be a 1/3 height to make it add to 1. I like it. All right, so if it is uniform, then I distribute a total probability of 100% amongst all the possible values. That means the height is going to be 1/3. All right, maybe. So then here, what would the probability that x, let me do it like this first. Let me not be too mean. 3 is less than x is less than 4.7. If you draw it, it becomes an area of a rectangle problem. That's almost too nice to believe that it's a part of this class. All right, so what do you do to get this? If I draw this, here's 3 roughly, bam. Here's 4.7, bam. What's the area of that rectangle going to be? So how do you get that? This is how wide? 1.7 times 1/3. So 1.7 divided by 3. 0.566. Which is really saying that this is a little more than half of the total block, is really another way to say that. So if I was just randomly throwing darts, all the darts that hit in this box, about 56% roughly would be in here. In that shaded area. That's all it's saying. Okay. So what if it was, let me see if I can push you guys a little bit.
Equilateral?
Yeah, let's say it's equilateral. Let's say it's actually doesn't. Let's just say it's isosceles at least, right? So it's symmetric. Is the key thing you're asking about. So how tall would it have to be? It can't be 1/4. What's the area of a triangle? 1/2 base times height. What do you want the area to be? Area's got to be a total area of 1. What do I know the base is? 4. So can you solve for the height now? 1/2, right? It'll be 1/2 of 4 is 2. Divided by 2, you get height has to be 1/2. You guys counting with me? Now, that's all I'm going to do with that one. Again, some of you guys are shaking your head no. But this truly is just geometry. If I want to force a triangle to have an area of 1, and I know its base is 4, you have to be able to figure out what the height is, right? Because you know the area of a triangle formula, or I'm going to assume you do, right? Any triangle is going to be half of some parallelogram. The area of a parallelogram is base times height, so that's why the area of a triangle is 1/2 the base times height. What's up? We all right? Oh, you didn't know where the area of a triangle came from? This is fine. It just means nobody ever took the time to show you, but that's all it is. That's why it's 1/2 base times height. The whole parallelogram is base times height. Any triangle is half of some parallelogram. Therefore, it's 1/2 the base times height. It's nothing amazing. I like it. I like it. All right, all right. So we're not going to see triangular distribution problems. Don't freak out. You with me? But I just wanted to show you, you could figure out at least how tall it would have to be because you just force the area to be 1. That's all you do. So why is this so nice? Well, this is nice because any little piece of it is going to be another rectangle. Okay, that's nice. But if I wanted this piece of this, what shape is that? What shape is that? Trapezoid. Oh shit! So you got to. Okay, that's a little bit more involved, right? You'd have to know how long this is, how long that is. So you'd have to know the equation of this line. And thank God we're not going to do that. I'm not going to make you do that. All I wanted to do here was show you I can have a lot of different shapes, and there are things actually that are sort of triangularly shaped. They are. So we can investigate probabilities of things within them. The same way we'd do this. But you're only going to see this kind of thing in that section of the homework. All right, no triangles. Don't freak out. Okay. So I could do almost any shape up there, really. But we want to go to the shape that is most often represented when we study. And it's not the only shape that could happen, for sure. But it's the one that happens the most often in statistics, is the normal curve, right? The bell curve. And I already said that we need some help with areas under this curve. Some of you guys had taken calculus. You don't have to have taken calculus to do this class. We just hired calculus people, and they did the work for us, right? So I'm going to give you today a chart, eventually, that's got, for example, we all should know, for a normal curve, what the area is between -1 and 1. So on a normal curve, what's the probability that I get a z-score between 1 and -1? 68%. Right? But if I ask you this question, okay, we ain't got shit for that. We ain't got nothing. We can give sort of a guess, right? But after today, we're going to be able to answer the question exactly. And I love it when somebody's like, well, why would I want to? Because you want to pass this class. And this class has uses, crazy uses. So we're finally getting to the point where we can really, really get deep into a problem like, how often do I change the filters in a hotel, the air filters? How often should I change them so that I'm always ahead, so that I don't have like more than half of them or something crapping out, right? How often should I change the light bulbs in a marquee in front of a theater so that I'm ahead of it, so that I'm not out there changing them when half of them gone out and people are like, what is that? What is that making a sign? What is that symbol? I don't know. That's, oh shit, I got to change all the light bulbs out. Are you guys with me? We'll be able to do that kind of thing with what we're learning now. Okay, so let me give you this here. This is the connection between what we've been doing and what we're about to do. So one side of it is this picture with a lot of normal curves. All right, don't worry about that side yet. We can't do that side yet because I haven't given you the other thing you need. I'm talking about this side with the histogram there in the middle. Well, let's look at that side first. You start over here for once.
You're like, can you do that for a quiz? That would be nice.
How you did it.
Moving down. I love this thing.
I'm still tripping on the fact that I thought those were the T and the M being
This is an exercise in futility.
I don't know where that.
But don't think that.
It's a slightly more brown.
All right, guys, let's do this first part together. At the top here. Just a little review of what we did last time. And it leads into the rest of the stuff here. So for this problem, tossing a coin 14 times. N is going to be what? That's crazy, 14. So it's always the number of times we're repeating something. Right? P in this case, of course, will be, we're assuming it's a fair coin, or we know it's a fair coin. And so Q has to be 50. Yes, sir. Say again? In this case, it doesn't matter because it's the same, but I am going to be looking for the number of heads. See the question? The probability of 9 heads. So P has always got to be what I'm looking for. Q is the other thing. No, it's if I would have said the probability exactly 9 tails, then I would have made P be the probability of tail. It's always the event that I'm looking for. Yes. In this case, it doesn't matter because they're both 50%. Yeah. All right, guys. So how do I set up the equation for that first question? Probably exactly 9 heads. How would I set up that equation? 14 choose 9. 0.5 to the 9th. 0.5 to the 5th. Now where did all that come from? I want 9 successes, so the rest must be failures. And hopefully some of you realize, just put 0.5 to the 14th because they're both the same base. If you don't realize that, it doesn't matter, because it doesn't happen all that often. Alright. So I'm going to be nice. I'm actually nice here on the handout too. If you haven't printed that calculator Bible, the calculator guide from the website, if you haven't printed it out for yourself, I don't understand you. But let me show you. I kind of was nice and put it up here too. Let's do this the full way out. So 14, how do I get to choose? Math. Probability. Choose. 14 choose 9. times 0.5 to the 9th times 0.5 to the 5th. So I have 14 altogether, right? Is that right? So I have 9 successes, and the rest are failures. And again, some of you guys might realize it's 0.5 to the 14th, whatever the hell I do for this problem. But just to make it the same as all the other ones we've done, we'll do this. It'll come out the same way. So we get this, 0.1222, basically. Now, who can help me with a nice way to do number 2? The probability of at least one head. Yeah, so it'll be 1 minus the probability of no head. We're going to catch up to what you just said. And how do I set up the equation for no successes? 14, choose none of them. So 0.5 to the 0. 0.5 to the rest. So no successes, all failures. How many ways is there to have 14 people and choose none of them? One way. So 14 choose 0 is 1. And what's anything to the 0 power? 1. Oh shit. And anything to the 0 power is 1. So that's right. What you said is perfect. 1 minus 1 times 1 times 0.5 to the 14. So just 1 minus 0.5 to the 14. But if you forget all that, you can just plug all that in your calculator. Calculator will spit it out correctly. So on my calculator, I can do 1 minus 0.5 to the 14th. You get 0.99994. So for us normal humans, that's almost impossible to not. Right? So probably at least one head is almost definitely, certainly going to happen. So if I do flip a coin 14 times and I do not get any heads, I get all tails, would that be weird? Yes, because there's a almost 100% chance I'm going to get a head, right? Okay, how we doing? We all right? Okay, I'll take that as an okay. This should be a review. Again, I want to remind some of you guys about something.
So number 1, how do you spell the I got it wrong.
Oh, so number 1 again was 14 math, probability, choose. 14 choose 9, and then 0.5 to the 9th times 0.5 to the 5th. Cool. So guys, if you have a question, at least 8 other people have the same question, right? So if you're looking around you and everybody seems to understand what's going on, they are lying. A lot of them are lying. I don't know why. Don't ask me why. I've been teaching for, good God, 18 years now. Holy shit. Yeah, I started teaching when I was 26. So I've been teaching for a long time, and every time I teach, people do this when they don't mean it. I don't know why. They want to make me think, oh, they know, and then when I grade the test, oh, they really don't know. It doesn't make any damn sense. So you don't listen to anybody around you. Yes?
Why did you put in 0? Like last class you did, you subtracted it after 1.
Oh, wait. So what did I do different now?
You put 0 in.
Okay.
Now why did you use 0?
Why do you use 0 here?
Yeah.
Here.
Yeah.
Okay. Because the probability of at least one thing happening, what's the opposite of that? The probability at least one does this thing. The opposite of that is, what's the opposite of at least one? If I said at least one student in here likes the uniform distribution, how would you show me that I'm wrong? You would show me that nobody does. So the opposite of at least one is none. And how do opposite probabilities interact? One of them is 1 minus the other one. Now, why do I want to do this? Because how many ways is there to have at least one head? We should know this better now. The first one could be ahead, and all the other ones failed. Or the second one, or the third one, or the fourth one. At least one could be two. So maybe the first two, or the middle two, or the first one and the eighth one, or maybe the third one and the fifth one, or maybe three. So maybe oh God. So I'd rather do the opposite probability where there is only one way to do it. Right? So I'm always going to do the opposite probability and do 1 minus that if the opposite probability has less work to do. Always. Right? That's a good way to do things. Do less work, I would say, is a smart way to do it. I like it. Yes?
I'm lost on how you got to the 1 minus 0.5 to the 14th.
So if you do it in your calculator, if you do 14, choose 0, the answer is going to be 1, because there's only one way. How many ways can I choose one person from 14 people? 14 ways, because there's 14 different people. How many ways can I choose nobody from 14 people? One way. I choose no one. And I walk away. Right? No one gets the rose. You all leave. Right? Horrible. That's the first show. That's it. That's the end of the season. Thank God. That's good. Does that make sense? So you can do the work. You can put the whole thing in the calculator, but anything choose 0 will be 1. There's only one way to not choose anything. I choose nothing. And I don't mean, I can do it like this. I choose nothing. Or you can do, I don't choose anything. Or I don't want it. No. There's one way to not choose anything, and that is to not actually take anything. I like it. I like it. And of course, anything to the 0 power is 1. So I got 1 minus 1 times 1 times 0.5 to the 14th. So it is 1 minus 0.5 to the 14th. Now, will you get the wrong answer if you put everything in there? Of course not. If you put 1 minus 14, choose 0, times 0.5 to the 0, times 0.5 to the 14th, you'll still get the exact same answer we did, because we put all this unnecessary 1 times 1 business in there, and the calculator still makes it come out right, of course. Is that cool?
Yep,
all right,
I got
I like
it. Thank you.
Sure. All right. So here's the shortcut on how to do, like, number 1. And this should interest you very, very much, because if you look here, right here where it says DISTR, see that above where it says VARs? By the way, I've got calculators if you want to borrow one. We're going to want some today. Does anybody need to borrow one? Check it out, make sure the battery's okay. They're starting to die. I got to get some new batteries. Okay, all right, let's see if we have enough. Oh, shit, okay. Okay. Alright. So here we go. You guys ready? Yes?
Why are we using this one?
Say again?
Why are we using that one for this question? Is it because there's only 2 questions?
Yeah, it's exactly. This is a binomial probability distribution. Why? There's only 2 outcomes. When you add the probabilities together, it comes out to be 1. All the trials are independent, right? If we get ahead first, does that affect the probability to get ahead on the next go? No. I like it. So that is officially a binomial probability problem. So that's the formula for it. Just like sum of x p of x. I only use that when I have it given to me as x and p of x, right? So this is the one I use in this situation when I have an n and a p and a q that I can find. I can use this formula. I like it. Let's see. Oh, so here's what you do. You go to second bar, so you get up to distributions, right? I'll let you guys do that. So right there where it says distributions, so hit second, that button, so you get to distributions. The first couple, how we doing? Everybody all right? Yes, sir?
Second is what then?
the vars button.
Bars?
Yeah, see where it says vars? Stands for variables.
Yeah, they said bars.
Oh, I'm sorry.
Oh, it's
Vars.
They got bars.
Vars. Alright, so everybody's at this point, right? So the first couple look like they're going to come in handy when we get to normal distributions. If you scroll down far enough, you find the binomial stuff. Now here's why there's two options. The first one is Binomial Pdf. So that's a particular value. Particular. So if I want the probability that there's exactly 9 left-handed people. Particularly 9. I want exactly 9. Right? C is cumulative. If I wanted the probability that at most 9 people are left-handed. That means 0, 1, 2. I want to accumulate everything from 0 to 9. That would be C for cumulative. The cumulative probability. Just like cumulative frequency distribution. Keep adding up all the probabilities. Are you guys semi with me? So to check number 1, I want Binomial Pdf. So if you choose Binomial Pdf, some of you guys with the older calculators is going to say Binomial Pdf with a parenthesis, right? What do I have to tell it? I have to tell it what n is, comma. For the old, anybody has it look like this? You don't need comma.